I'm here to talk about Gleam. Oh, it's not very pink on that one. Okay. I'm here to talk about Gleam, which is a new statically typed programming language for the Erlang virtual machine that I've been working on for the last 2 or so years. And Gleam draws inspiration from both Beam languages, such as Elixir and Erlang, but also from ML languages, such as Haskell and Elm and OCaml and all that good stuff. So in this talk, I'd like to take a look at these 2 families of languages and see why I think they're really fantastic to work with. What are some of their strengths, or maybe what are some of their weaknesses, and how Gleam, this new language that I've been working on, attempts to unify these 2 things together. And then, lastly, a bit more of a mundane look at sort of where Gleam is going next, in case you want to have a go. And then maybe some time for questions. Cool, so the first question, why Erlang? I think that one of Gleam's greatest strengths is that it can pass to Erlang, and thus it can take advantage of all of the wonderful things Erlang has to offer, which begs the next question, what wonderful things does Erlang have to offer? So a large part of the answer to that question is the Beam, which is a word I keep hearing an awful lot today, the Erlang virtual machine. Erlang is unusual for an older functional programming language, is that it doesn't come from academia in any way. It originated largely from industry. Back in the 80s, the telephone company Ericsson were looking for the ideal language to write the firmware for their telephone switches in. And from this real-world set of requirements, this new language, Erlang, was born. So a telephone switch is a piece of hardware that connects up phone calls. So when a person dials a number on their phone, their local switch identifies where the call is trying to get to, and then it creates a complete circuit between the caller and the receiver. So back when the first telephones were invented, this would have been a person sitting in front of a switchboard connecting up circuits with lengths of wire. And then sometime after that, technology progressed a little bit and it moved on to automated mechanical machines that would still connect up pieces of wire. And then after that came digital switches that would form virtual circuits inside software. And it was in this world of digital switches and virtual circuits that Erlang came to be and it was created for. And so in order to meet the unusual set of requirements that you find in this telephony world, Erlang and the Beam developed a slightly unusual set of features. So for a telephone switch to be useful, it needs to be able to support multiple phone calls at the same time. If you had to wait for your neighbor to get off the phone before you could make a phone call, I suspect telephones probably wouldn't have caught on in the way that they did. And because of this, Erlang needed to have great concurrency features so that the switch could handle multiple calls at the same time. Any program written in Erlang needs to be able to trivially perform a great number of tasks at the same time. And this was such an important feature that they ended up naming the language after it, because an Erlang, as well as being a programming language, is a unit. And Erlang is a unit of concurrency. It measures seconds per second. So if you have a telephone switch that can hold 100 simultaneous connections, you have a telephone switch rated at 100 Erlangs, which I think is pretty cool. So how well does it scale when it comes to concurrency, if this is actually what the language is named after? So let's look at some real-world benchmarks. EachAppetit, this is a WebSocket-based chat server, a fork of which I believe powers WhatsApp, which is the popular chat app that is owned by Facebook. And in their benchmarks, they found that a single EachAppetit instance running on a single machine could hit 2 million active connections, which is quite a feat, I think. And another interesting fact is that WhatsApp are able to scale this EachAppetit-based platform with 900 million users with a team of 50 engineers, which I find absolutely incredible. I can't do anything with 50 engineers. So Felix Channels is another thing, another system written in Erlang, written in Elixir. It is a WebSocket-based pub subsystem with sophisticated presence features. And in their benchmarks, the Felix team also scaled to 2 million active connections on a single machine. And even when operating at this load, they were capable of publishing an event to all of the connected clients in under a second. So a common feature between this benchmark and the previous benchmark is that they both reported the Beam as not being the limiting factor, or not the thing that was causing them problems. They actually had more problems with the underlying network hardware. They had more problems with the Linux networking stack, because it turns out it's actually somewhat difficult to open and use 2 million TCP sockets on your average Linux server in the cloud. And lastly, in a somewhat more contrived example, the Erlang team at Ericsson, so the team who are actually making Erlang, they tested to see how many threads they could spin up in a single Erlang program. And on a computer with just 16 gigabytes of RAM, they spun up 20 million threads without a problem. And during this benchmark, they found it took 5 nanoseconds to create a thread and 6 nanoseconds for any one of these threads to respond to a piece of work. And this was back in 2005, so computers have got more powerful, and the Beam has been developed further since then. We can go even further, which is quite exciting. So when it comes to concurrency, the Beam can definitely scale, but it's not good enough for it to be merely possible. Ericsson needed it to be relatively easy, so their firmware developers could be as productive as possible. Asynchronous programming is notoriously difficult, especially if the tools that you have at hand are locks and callbacks and shared mutable states. So the creators of Erlang went down different routes. Rather than having a small number of threads handling a large number of tasks, they instead decided to have a large number of threads, but each one only does one single task. So if each thread only has to do one thing, you can write it entirely in a sequential fashion and not worry about asynchronicity. The programmer doesn't have to write any asynchronous code at all when they're doing their business logic. So to paraphrase the late Joe Armstrong, the creator of Erlang, it's very difficult to write a web server that can handle 2 million sessions. But it's actually very easy to write a web server that can handle 1 session and then just run 2 million copies of it. And so to support this level of concurrency, Erlang threads are not operating system threads. Instead, they are lightweight threads implemented within the Beam called processes that run on their own schedulers. And back in the late 80s, computer processors only had a single core, generally. So Erlang programs were highly concurrent, but they were still single-threaded. And when processors started to arrive that had multiple cores, the Erlang runtime was upgraded to make full use of all these cores and to spread all the processors across all of the available computing power, making full use of the processors. So almost overnight, Erlang programs went from being concurrent and single-threaded to being multi-core with hardly any intervention from the programmer. Sadly, the processors in telephone switches are not quite as isolated maybe as the ones inside a web server. They need to talk to each other in some fashion. In most programs, there's going to be some way in which the different concurrent parts of your program are going to need to synchronize, they're going to need to communicate. And so to facilitate this communication, they didn't use shared states. They instead send messages between processes. What's more, these processes inside a telephone switch don't just need to talk to other processes within the same telephone switch. They also need to talk to different pieces of hardware all across the network, as a call is routed from switch to switch, from piece of hardware to piece of hardware, in order to make the full circuit. So to facilitate this cross-network communication, the Beam has distributed computation features built in. So when sending a message, it doesn't matter if the two processes are living on the same instance of the virtual machine, or you could have 2 different instances of the virtual machine running on the same computer, or they could be running on 2 completely different computers connected by a network. And to your code, it all looks exactly the same. The only thing that's different is perhaps the latency and how long it takes to send those messages. So because distributed computing is built into the Beam, a typical Beam program written in Erlang or Elixir or Gleam can be turned into a distributed program that runs on a cluster of network computers with minimal efforts. Garbage collection is important. So the people at Ericsson didn't want their programmers to be dealing with manual memory management because it's error prone, and they don't want to risk having problems with people making mistakes in that area. So the Beam implements garbage collection, but this poses a problem, right? Because typically runtimes will pause all computation in order to perform garbage collection, but here that's not an option. The switch can't just pause all calls for a second while it sorts out memory and then resumes it. People want to continue having conversations. So instead of performing global garbage collection that stops everything, the garbage collection is performed by the Beam on a per process basis. The only thing that's stopped is the individual processes that need to have their memory cleaned up. And because you only have, say, perhaps a millionth of your program being paused at any one time, you don't have any stops, which means your latency is predictably low. And for me, most excitingly, Erlang processes act like error bulkheads. They contain problems. So when something does go wrong and your code crashes, the problem is contained to the smallest possible subsystem within your code, and it will not impact any of the other work that's happening in your wider program. So an Erlang program that takes advantage of this property can self-heal by, in a controlled fashion, restarting the process, and hopefully it will succeed now that it's shed whatever corrupt state caused it to fail in the first place. So in this way, you can think the Beam is actually kind of similar to the popular container orchestration tool Kubernetes. But what makes the Beam different from Kubernetes is that this state shedding can happen at a much more fine-grained level within your application. We don't lose the entire program and every, for example, request that it's currently serving. We just lose the single one that caused the problem. So you can imagine the relationship between the Beam and Kubernetes being kind of similar to the relationship between Kubernetes and region failover in your clouds. They're similar, but they operate at very different levels of abstraction. So the Beam was created with telephony in mind. But it turns out what was quite a niche set of requirements back then is actually surprisingly commonplace today, like concurrency, parallelism, distribution, achieving a consistent low latency, and being fault tolerant. These are all things that we want in network services today. It's not just telephone switches. So the Beam has become, by accident, a really wonderful platform for building web applications and databases and message queues and all sorts of things that we as developers, especially web developers, deal with on a daily basis. So that sort of, to some extent, explains why I think Erlang is really exciting. And you should hopefully see now why I think the Beam is a really wonderful platform, but I've not really answered the question of like, why Gleam? Why create a new language at all? There's already several fantastic languages on the Beam, which I encourage you to try, namely Erlang, Elixir, and LFE. Well, why not just use one of these rather than spending 2 years in my bedroom making this thing? To answer this question, I want to take a little bit more of a look at that last point of fault tolerance and see how does Erlang's fault tolerance affect us as developers of software, and how does it affect us as operators of software? So hypothetically, let's imagine a situation. It's a normal day at work, and I'm working on my Erlang web application, and I've been tasked to make a change. Perhaps I'm adding a feature, fixing a bug, I'm making some kind of change. So I spend some time editing my code, making some changes. Once satisfied, I run the compiler to see if it emits any warnings or errors, and it says, no, that's fine, no problems. After that, I can run the unit tests on my laptop to see if I've caused any breakages. But they all come back green, and I can push my code up to GitHub. And once uploaded, the code triggers a build on a CI server. It runs all the unit tests, all the integration tests, runs some linters, static analysis tooling, anything to try and find any problems with what I've done. To spot any mistakes. If all those checks pass, I can then move on to deploy my application to a staging environment. And on the staging environment, I can manually test what I've done to see if it looks good to my eyes. And then I can demo the behavior to maybe my team or some stakeholders to see if they're happy with it. Meanwhile, there's a code review process. So on GitHub, my code is being looked at by some of the programmers inside my team because maybe they've got some context that I haven't. Maybe they know something about the application I don't. And they can find something that's going to cause problems further down the line, or they can find some way in which it can be improved. But in this instance, they're happy, and they merge the code to master, which triggers another CI build. So the same thing happens again. All the tests run, the linters run, just to make sure there's no problems in the merging process. And lastly, once all the tests are passed, the code is deployed to production and then released to the users. Satisfied with the job well done, I pat myself on the back and I go to lunch. But then disaster strikes. Users are emailing and saying, there's something wrong with the application. It doesn't do the thing it's supposed to do. So right at the beginning, when I was editing the code, I made a mistake. I introduced a bug, and it slipped through each link in this chain that was supposed to give us safety. And now it's snuck into production. So luckily, the application is written in Erlang, so it's not a catastrophic problem. It's been self-contained somewhat, but there still is a problem in production. And I, as a matter of urgency, need to do something about that. I love this slide. In this instance, the problem was discovered just a few hours after I made a mistake because this pipeline's pretty slick. But and as a result, the code is still fresh in my mind, and it's quite easy to work out what the problem is and how do we fix this. But that's not always the case. Depending on the culture of the company, I'm working at or you're working at, it might take days or weeks for a change to make it into production, or it might take longer for users to discover the problem. So I work at a bank at the moment. The idea that we can get something deployed in weeks is kind of phenomenal. By the time it's come round, I've completely forgotten what I've done in the first place. And in the worst case scenario, it's been months or even years since the bug was written, and it was written by somebody else who has left the company and gone somewhere else. And now I've got this bug report, and I've got to try and work out what the problem is and fix this code that I've possibly never even seen before. I possibly don't even know what it's supposed to do. So the larger the gap between making a mistake and the mistake being discovered, the harder it is to fix the problem. This obviously isn't the only problem in how difficult something is, but it is a multiplier, and I think it's very important. So Erlang gives us really powerful tools for tolerating mistakes. It gives us really powerful tools for debugging mistakes once they're in production, but this only helps us once they're in production. The time cost and loss of familiarity is expensive. This is far from optimal, and I think this is an area that we can improve with Erlang. So what I really want is for problems to be detected here. As soon as I make the mistake, I want a feedback loop that triggers and says something's wrong. I want it to be as fast as possible so we can spend less time doing exploratory work, spend less time rummaging through the code to try and find what the problem is, and more time iterating, more time delivering business value, more time having fun, making new things. Debugging isn't fun sometimes. So Gleam aims to provide this fast and safe feedback loop by introducing a type system inspired by those found in the ML family of languages. So why these languages? It's because I believe that these are the ones that do best at providing this rapid feedback loop for rapid prototyping. And maybe that's slightly controversial, but I'm going to show you some quotes which I think explain a little bit of why that is. So Messenger is Facebook's web chat program. It has a staggering 1.3 billion monthly users. And back in 2016, they started converting it from Java. Well, they started converting the web client from JavaScript to Reason, which is a dialect of OCaml. A year later, 50% of the code base was written in Reason, and they had this to say: Messenger used to receive bug reports on a daily basis, and since the introduction of Reason, there's been a total of 10 bugs. That's during the whole year, not per week. Refactoring speed went from days to hours to dozens of minutes. That's quite an impressive statement, I think. NoRoad Inc., they're a company in the United States that build educational software. So back in 2016, they started Elm, another similar language, to their JavaScript web application with great success. And in 2018, one of their engineers, Richard Feldman, posted this tweet: after 2 years and 200,000 lines of production Elm code, we finally got our first production runtime exception. In that period, our legacy JavaScript code has crashed a mere 60,000 times. So this is not to say that the engineers at NoRoad Inc. or Facebook are superhuman or they're without error. They definitely make as many mistakes as you or I do. They're just people. So the key takeaway here is that they've found some way of discovering and fixing these problems before they get to production. They've shortened that feedback loop. And lastly, Luminara, a company that provide eco-friendly branded packaging for online stores. And in 2018, they started converting their JavaScript front end to one written in PureScript. And after a few months of PureScript in anger, Brandon Martin, one of their engineers, had this to say: I've had such a positive experience with little mental overhead and total trust in the compiler. I implemented an entire page with a list of data, filters, search, and pagination, which worked first time. So the thing I really like about this is this idea of having a feeling of trust in the compiler. It's something that can be relied upon. And with Gleam, I want to create a similar experience for the Beam. I want the compiler to be thought of as like a pair programming partner, whose job it is there to help you catch your mistakes and provide additional context that you don't have immediately to hand. So how do these languages achieve this? They do it by having a compiler that's capable of analyzing code for inconsistencies. And then once they found these inconsistencies, they can provide precise feedback detailing every place inside the code where a problem can arise. And so once we have this information, the programmer can change the way they write code. So first, the programmer makes an edit, informing the compiler of the kind of change they want to make. So for example, say a function has been changed to sometimes return a nullable value. In languages like Erlang, where you don't have this help, it's up to the programmer to determine all the places that you need to change in order to incorporate this, this new nullable value. So in Erlang, I'd probably use a mixture of existing unit tests, which hopefully would catch some of the problems, and my own familiarity with the code base. These sort of things would aid my search, but it would still be very much a manual search following the code. So in Gleam and ML languages, the compiler outputs effectively a to-do list. And the programmer just has to go through the lists one by one and correct each place and tick it off. There's no need to do discovery work. There's no need to do exploration. Just state the change you want to make to the compiler, and the compiler shows you then what you need to do next to integrate that with the rest of your code. And I think you can achieve the same effect with a really thorough set of unit tests, but I think this system's got some advantages. So we don't have to write the tests. The compiler does the checking for us. A static analysis can be thought as free, full unit test coverage without having to do an intervention. And this even covers code that is traditionally quite tricky to test. So for example, code that does I/O, where you might need to mock some kind of external service in order to get the same effect in your tests. Secondly, it's really fast. It just needs to traverse the code base once. While a large code base you could probably check in seconds, while tests could possibly take minutes. And thirdly, the compiler can provide much more precise information about the location of the actual problem itself. Tests only ever give you the location of a resulting symptom. Once a test presents an error, the programmer then has to do some exploratory work in order to discover, is this actually the location of the problem, or is this just a symptom of a problem further down the line? So it might seem that with this MLstyle error detection, the Beam's runtime fault tolerance and error handling features are somewhat redundant, but I think they can complement each other quite nicely. So the error detection means that we're aware of all the places in which you can have a problem in your application, and then we can make an explicit decision about how we want to deal with each one of these problems. And because the decision about how we want to handle an error, how we want to handle a problem, is explicit, the compiler can tell if a potential crash is intentional or not, or if a mistake has been made. So this isn't particularly clear, so let's look at some examples. So imagine a problem caused by a mistake caused by me. For example, I'm trying to reverse a binary string here, but instead I've mistakenly used a function that reverses lists. So in this case, once the compiler's error detection highlights this problem to me, I realize that I've made a mistake, and the most obvious thing to do is just to correct that mistake. Erlang's fault tolerance here isn't useful. Once we found these mistakes, we want to find them and we want to fix them. Another situation in which errors might arise is when dealing with user inputs. So here, this is a handler function inside a web application. It takes a request data structure, and then it performs some computation, and then it returns a response data structure. And as part of that, it reads some data from the request body, and this data has been encoded as JSON. The problem here is that the request body might not always contain valid JSON. We can't always rely on getting the same output, the same input from the outside world. So once this problem has been highlighted to us by the static analysis, by the error detection, the most practical thing to do is check whether or not it's valid JSON, and then if it isn't, we can return an error message back to the user, informing that there's something wrong with the JSON message that they sent. If we can pass an error back up a chain to a user, that's probably the best thing to do. We don't need to crash. We don't need to use the fault tolerance. So third example, I used to work at a video transcoding startup, and we used to have lots of jobs that run in the background. And as a result, they didn't have a user immediately attached to them. They just run off somewhere else. So one of the jobs did like this. First, it looked at some metadata from a database. Then it created some thumbnail images, so we can show in the web UI. And lastly, it transcoded the video into some other formats. So each one of these steps is expected to succeed according to our business logic. You should always be able to make thumbnails. You should always be able to transcode video. But because of the nature of the universe, this might not actually be the case. There's a very real chance that even though we think this should always work, it might not always work. So for example, a faulty hard drive could corrupt a video file, or the unreliable network could result in the database lookup timing out, or there could be a bug in the third-party transcoder that we're using and it could crash. So the MLstyle error detection forces the programmer to acknowledge this. You have to deal with these potential problems, and if you naively incorporate it, you end up with this rather nested and hard-to-read code. After each step, the programmer has to check to see whether it's failed, and then do something with the error if it's present. So this code is much less clear, I'm sure we'll all agree, and the business logic here is being obscured by all the error handling. So it's possible to rewrite this ever so slightly using some higher order functions that extract some of the conditional logic. And this is a little less nested. Maybe it's slightly easier to read, but the reader now needs to be familiar with all these additional combinators in order to know what this function is actually doing. And it's still considerably more complicated than the initial code that didn't have the error handling. To make matters worse, it's really not clear at the end here, when we match on the final results, what actually do we do with the error? Because there's no user, we can't show this to anyone. Perhaps we need to implement some kind of retrying mechanism and some kind of error logging system. And I'm hoping that if any Erlang people in the audience, they're bursting to jump forth and say, no, there is a better way. We don't have to do defensive programming like this. There is an alternative. And that alternative is to do offensive programming. If your business logic says, this should never fail, and if something fails here, it has gone horribly, horribly wrong, and there's nothing we can reasonably do about it, then don't check for the error. Instead, say, I'm asserting that in order for us to continue, there must have been no error. And if there was an error, we crash the process, because there's no way that a process can reasonably continue doing its job in the event of this catastrophic failure. And now the Beam's fault-tolerant properties become really useful. So we can, the Beam will log the error for us, it will report it, and it will gracefully resume your work, restarting the process so it can try again. And so as the Erlang saying goes, you should let it crash. So the MLstart type system helps us find all the places in which errors can happen and which problems can arise. And then we can categorize the errors into two different types. So there are errors which are expected within our domain. This could be, an example of this could be invalid user inputs. We want to deal with these locally using conditional logic. And then there are errors which are exceptional outside of our domain, something we don't think should ever happen, but could because the universe isn't kind. These need to be handled in a non-local fashion using processes and the Beam's fault-tolerant properties. If your error is truly unexpected, it shouldn't get in the way of your business logic. You shouldn't have to write extra code for your problem to be able to tolerate and survive these unexpected problems. So hopefully that gives you a little bit of an idea of where I think the value is in bringing these two families of language together, and hopefully what we're trying to achieve with Gleam, or at least what I'm trying to achieve. So I want to step back a bit from philosophy now and take a bit more of a mundane look at Gleam and where it's going next. So Gleam as a language, as a compiler, as a standard library is ready to be used in people's projects. However, many of the niceties I think we've all come to expect from a programming language don't really exist there, so it's quite hard to be productive in it. And so what I want to do right now is to focus on getting everything that's required for Gleam to be a productive language, and so people can start having fun of it and maybe start using it in their pet projects. And then once that's done, we can start looking at maybe more exciting language extensions. So we want the experience of writing Gleam code to be as productive as possible. And so no matter what editor you're using, So to achieve this in Gleam, we're going to implement the language server protocol from Microsoft. So once we've implemented this, Gleam programmers will have high-quality IDE-like features no matter what text editor they're using. So you can continue working however you like to work. And what's more, because Gleam has a focus on static analysis and type inference and error detection, Gleam can provide much richer and more in-detail information inside the editors than is possible with any conventional Beam language today. So another, probably more important but less sexy part of the puzzle is documentation. And I don't know if anyone has tried to write any Gleam yet, but it's not as easy as it should be, because there's no way to actually know what functions and modules are available for you, unless you want to go read the source code. So if you compare that to Elixir, which is another relatively young language on the Erlang virtual machine, they have really beautiful, searchable, mobile-friendly documentation, which is generated from the code itself. And then it is hosted on Hexdocs, which is a unified documentation site for programs running on the Beam. And it is integrated with the Beam's package management system, so you can easily find it from your code. So in Elixir, it's easy to find the documentation online, or in the command line, or even inside the program itself. And so we intend this to be the case for Gleam as well. Exism. I don't know if anyone's used Exism, but it's a really lovely place to learn new languages and to practice your coding skills. So how does it work? A programmer picks a language they're interested in. So I guess Ruby here, because I wasn't smart enough for Photoshop to edit the Gleam logo in there. And then they ask Exism for an exercise. Exism gives them an exercise, and that has a set of instructions, some skeleton code to fill out, and a set of unit tests to make pass. And once you've completed that, you send it back to Exism, and you get friendly, constructive advice from your peers and from track mentors. And then you can view solutions from other students, so you can compare your work to others and learn other ways of solving the same problem. So Exism has 51 live language tracks, and they've given a thumbs up for a Gleam one. So exercises need to be ported over to Gleam, and some documentation needs to be written. But once we have that, we've got an excellent world-class experience for learning Gleam. And Exism is open source, it's community run, it's extremely well organized and very friendly. So if you're interested in Gleam or just learning any language, I really do recommend talking to the people at Exism. On Linux, that's colorful. Okay. As I said before, Gleam's greatest strength is that it builds on top of Erlang. And as such, we want to incorporate with and enrich the Beam community as much as possible. So Gleam uses the standard Erlang build tools and package managements. We don't want to create an alternative. We don't want to fragment the ecosystem. And it's straightforward to use Erlang libraries from Gleam, giving us a really healthy ecosystem of battle-tested packages and libraries to use in our programs. We also want to give back to the other Beam languages. So it should be just as easy to use libraries written in Gleam in Elixir and Erlang and LFE as is in any other language on the Beam. An Erlang programmer should just be able to import a Gleam module and then just use it straight away without having to modify their build pipeline or learn anything about Gleam. It should just be another Erlang module. So the aim is for Gleam to enrich the ecosystem further for all Beam languages, and possibly provide a new way of programming on the Beam, which could make it more attractive to a wider collection of people. So yeah, that's all I've got to share today. If any of this sounds interesting, please do check out the website, and feel free to message me on IRC, GitHub, Twitter, catch me in the hall, and ask me any questions you might have. Lastly, I want to say thank you to Griffix, who is an amazing artist who made the logo and Lucy the star. Check out his website. It's got loads of really fun, playful arts. Thank you very much for listening. Any questions? For sure. So I'm less interested in a type system for the idea of safety. I'm much more interested in a type system as a way of providing fast iteration. And Dialyzer, while a truly incredible piece of engineering, I don't think it meets that requirement because it is incredibly slow. So Dialyzer was built with the set of requirements so that you can apply it to an existing Erlang code base. And if the code could be correct, then it says that's okay. It's only if it is 100% sure that the code is broken that it reports an error. And detecting this is really expensive, takes a long time, and allows you quite a range of possibilities which still allow errors to sneak in. So what I wanted is basically the exact inverse of Dialyzer. I want it to be incredibly quick, I want it to be incredibly strict, and I want it to show me the singular path through whatever I'm doing so I can be confident it works without having to do lots of manual testing. Gleam is not written in Gleam. Gleam is written in Rust. I would love to write it in Gleam one day, but there's a few problems such as how do I bootstrap it, and the type inference algorithm, Hindley-Miller-Damas, the implementation I'm working with uses quite a lot of mutable states, and I've tried implementing that in Erlang a few times, and while it does work, it's quite awkward, and having a language that does have mutable state makes this much more comfortable. Also, Rust is incredibly fast, so that's really nice. Could you give an example of what sort of things you might be interested in? So that's just really exciting, really interesting, and I think there's a lot of stuff you could apply to how do you type concurrency and processes and messages, etc., which would be a fantastic area to do future research. But I'm sort of deliberately choosing not to do that because I'm focusing on these really mundane things for the moment. Because I've seen I really want there to be a typed language on the Beam. That would be my absolute dream. And I've got really excited about Alpaca and various other, and Gradualize and all sorts of other projects try to do this. But they seem to, from the outside, it seems like they keep running into a block where they get sort of a lot of the basics going, and then they come to the point they want to make a really robust system for typing OTP and processes and messages and this sort of thing. And then they try something and maybe it doesn't quite work, and then they retreat and start researching, and then they never return from the library. And so what I want to do is I want to get, 95% of Erlang code is synchronous, right? So I really want to get that down and get us to start being productive there. And if we have to resort to using the level of safety that Erlang offers us when it comes to concurrency, that's fine, because we've still gained a lot. But once we've got that down, we've got all the nice productivity stuff down, we can then start working on how do we extend this further. Right now, definitely not. I aspire for it to be that because I put a particular emphasis on trying to make the tooling and the error messages as friendly as possible. I really want it to be that you declare that this change is going to happen, or you make a mistake and it says, here's a problem, here's how you might fix it. So I think once this is more mature, it could possibly meet that. But right now it's difficult because, for example, there aren't really any documentation. If you're going to any program that isn't absolutely tiny is probably going to use a lot of interop with Erlang libraries. So you're probably going to want to have some familiarity with the ecosystem in that way. But in future, I really do hope so.
Can you use server as
Yes. There's no first-class support for processes or OTP in any way, but we do have quite flexible FFI in which you just state there is a function or a data type that exists in the world. It's of this type. You can treat it like this, and then Gleam just trusts you. And then whatever you do on the Erlang side is fine. And so using that, I've written some bindings to Gen Server and Supervisor, for example, and they're enough to do to write typed concurrent programs in Gleam. However, they're not quite flexible enough in order to replicate all of the patterns that we use in OTP if we use in Erlang, because it's very dynamic by its very nature. So there's always going to be some sort of friction between, being able to use the patterns we're used to in Erlang and being able to give you type safety. So exactly where that's going to fall, we don't know. But it's just writing libraries. So you can do it, yes. Okay, so the lion's share of the code has been written by me, but there's been lots of people sort of like orbiting around and either volunteering information to me or I've gone and pestered them. Like quite a few people in the Elixir core team have actually spoken to me at some length about this because they also have a real desire to have some sort of types on the Beam. They want to do it in Elixir, but they don't have the luxury that I do of having a clean slate. They need to be able to apply it in a way which is backwards compatible with a language that's been around for 7, 8 years or something like that. So they've got a much more difficult problem, and so we've been communicating a bit. I really I really enjoy open source community work. So if you want to do stuff, please either message me or grab me outside or message me on IRC or look at the GitHub. There's lots of issues that are tagged with ones that are beginner friendly or ones that I think would be good for people to pick up. Or just download Gleam and start writing things and try and make some libraries and tell me what you found problematic. That'd be cool. Anyone else? Cool. Thank you very much.